In this video, I'm going to be discussing solubility in some detail. And in particular, I'm going to be talking quite a bit about the thermodynamics of solubility. But just first, some basic definitions here. So a solute is the thing that is dissolved in something, so it is the dissolved substance, and a solvent is the dissolving medium. So solutes are dissolved in solvents. And so when we want to say that something is soluble or is insoluble, this is kind of a continuum. I think a lot of people at the general chemistry level especially think that solubility is this black and white thing. Something is either soluble or not soluble, but it is very much a continuum. Some general rules here that we can think of. Something can be considered soluble if at least zero point 0.1 molarity can be dissolved into it. So if we can at least get a solution of 0.1 molarity, or at least zero point 0.1 grams per milliliter. Slightly soluble is going to be between 0.001 molarity and zero point 0.1 molarity, and insoluble is generally anything less than 0.001 molarity. So if you can't get a concentration higher than this, then we would consider that insoluble. Again, these are rules of thumb. These are hard and fast things, but this is just kind of a way we can think about solubility. And so when we think about solubility, a lot of times we're thinking about dissolving something like a salt in here. So we could have our cation and our anion, A and B here, and then that splits apart and becomes dissolved in whatever the medium is. And so the constant for that, the solubility constant, is this Ksp, which is just equal to the concentrations of our dissolved species here multiplied by each other. All right, so solubility, as I said, is about thermodynamics. This is kind of a rule in chemistry, period, that it's all about thermodynamics, but solubility is about thermodynamics. So we have our delta G here, which is our Gibbs free energy, and that is equal to the negative R times T, which is our gas constant times the temperature times the natural log of our Ksp. And the delta G here is equal to our enthalpy minus the temperature times the change in entropy. And so if we use this right here, we can derive this equation like that, and we can also obtain these equations here. So these are all just ways that we can relate these thermodynamic quantities, namely the Gibbs free energy, the enthalpy, and the entropy, to our equilibrium constant Ksp. And so we can see that this is, as I said, all about thermodynamics. And so delta G being negative means that it is spontaneous, and so that's going to mean that it dissolves, and delta G being positive means that it will be non-spontaneous, and so then it would not dissolve if our delta G was positive. And so we want to look at these two terms here, the enthalpy and the entropy, since, as I said, this is going to be what our solubility is based on. So we want to look at this delta H and this delta S to determine whether the delta G will be negative or positive, which would tell us whether our dissolving is going to be spontaneous or not. And so the enthalpy is going to be about the breaking and forming of intermolecular interactions. So our solute molecule, we're going to be breaking interactions between them and then forming interactions with the solvent when we dissolve. Then the entropy is about how the molecules arrange themselves with respect to one another. And so that will get into what's called the hydrophobic effect. But first I'm going to talk about the enthalpy. So as I said, it's about breaking and forming bonds. And so we want to look at bonds here, meaning the interactions, the intermolecular interactions here. And so we want to look at whether these things are polar or nonpolar. So in the video that I did on solvents, I went over things like the dipole moment and the dielectric constant, which are measures of the polarity of a molecule to tell us whether we can consider it polar or non-polar. And so these are not extremely good measures of solubility. For that, we like to use what's called the partitioning coefficient, which I did talk about in the solvents video, and I will cover again in this video. But these are some measures of whether something is polar or not. And so the polarity is important because that will tell us about the types of intermolecular forces that our substance can engage in. And so I put these here in descending order of strength. So the strongest is ion dipole, so that's the interaction of a full charge and a partial charge. So something like a sodium ion with water would be an ion dipole. Hydrogen bonding, so this is a dipole-dipole interaction, but it's a specific kind that has to do with hydrogens on the most electronegative atoms, namely nitrogen, oxygen, and fluorine. And so we have to have a hydrogen bound to one of those atoms. And again, this is just a dipole-dipole interaction, but because it's very strong, we call it something different. So we give it its own category because of how strong of an interaction this is. Then everything else that's dipole-dipole, we just put in as dipole-dipole. So these are interactions between molecules with partial charges. Ion-induced dipole, so in the presence of an ion, a dipole can be induced on a molecule, and we have dipole-induced dipole, so in the presence of a dipole can be induced on a dipole. So a lot of treatments of these intermolecular forces will even leave these two things off because they're not as important. They are important to, that's why I list them here, but a lot of times, as I said, you'll see those just left off of this list here. And so then our weakest force is the London dispersion force, sometimes called the van der Waals force, and this is the transient dipoles interact with one another. So we are talking about molecules which are quantum mechanical systems, and so the electrons that are orbiting them are more like clouds. They can have these transient dipoles show up, and then those transient dipoles will interact with each other and induce dipoles on neighboring molecules. So that's kind of an important point here, is that they are, in a way, sort of dipole-induced dipoles, but they are sort of the weakest version of dipole-induced dipoles because they are transient dipole inducing transient dipoles in other molecules. And so these are just some polarities here on molecules. So we have ethanol, which has a dipole moment of 1.69, acetone is 2.88, and water is 1.85. And so we can see here why this is an imperfect form of talking about the polarity of a molecule, because acetone actually has this higher dipole moment than water, even though we consider water to be a more polar molecule. And so that's why we can't always trust these dipole moments to tell us about the solubility and solvent activity of these molecules. And so that's why we usually use an empirical measure like the partitioning coefficient. All right, so as I said, the enthalpy is about the breaking and forming of bonds, where the bonds can mean the intermolecular forces. And so we can think of an example. So if we have this potassium chloride, we are breaking this into two different ions here. And so this is going to have a positive delta H because we have to put energy into it in order to break these bonds. We can think of these like magnets. If you want to pull them apart, you have to put energy into it. You have to actually flex muscles and use energy in your muscles to pull those magnets apart. And it's a similar analogous situation when we're talking about these ions where we have these charges and we have to pull those apart, and so we have to put energy in to do that. But this is favorable as far as entropy is concerned because we're going from something that's more ordered here to something less ordered right here, where we have broken it into two things, and so we have more microstates that we can go through, and so that is entropically favorable. Then we have the interactions of these ions with the solvent, So this is the second step here in dissolving this. So I've kind of broken down the dissolving of KCl into two different steps here. The first step is breaking it apart. The second step is the interaction with the solvent molecules. And this is where we're going to get the favorable delta H here, because we are now forming these ion dipole bonds here with our water molecules. And doing that is enthalpically favorable. And so we'll do that with both the potassium and with the chloride, where the potassium will interact with the partial negative oxygens and the chloride with the partial positive hydrogens on here. And so that is, as I said, enthalpically favorable, but it is entropically unfavorable because we have to make these alignments of these water molecules with these ions. And so that's creating more order here. And if you want to think about it a little bit more rigorously, it's reducing the number of possible microstates. And so that is reducing the entropy there. And so we have this trade-off here where we have a process that is enthalpically unfavorable but entropically favorable, and then another process which is enthalpically favorable but entropically unfavorable. And so we are going to be putting those things into our equation up here, remember. These are the things that we are thinking about. And so we want to put those things into this and see if we get a delta G. And if we do get a negative delta G from that, then this is going to be a spontaneous process and it will then be soluble. So we can also think about this when we are looking at a non-polar solvent. So again, we have to put energy in to break this ionic bond here. So again, this is going to be enthalpically unfavorable but entropically favorable. But then we are going to try to mix this with our solvent. And so here I'm using hexane. And this is again going to be enthalpically unfavorable because there are not very good interactions here. And it's going to be entropically unfavorable. And so that's why there's not going to be any dissolving of this KCl into hexane here. And so if we have a non-polar solvent, we are not going to get dissolving of this salt in it because this is energetically unfavorable in both cases. So the only place where we are getting something favorable is right here, and that's going to be far outweighed by any of the other unfavorable thermodynamic interactions here. And so this is just kind of thinking about the same thing but in a slightly different way. So we have what's called the lattice energy here, and then the heat of dissolution. So those are the things that I've been looking at up here. This is our lattice energy here. And so the lattice energy is the energy we need to put in to break up this crystal here. And then the heat of dissolution is we have the solvent here and then our solute, and then we want to mix those together. And so the delta H for this is just going to be the heat of dissolution plus the lattice energy. And so we want this to be more negative than this right here if we want it to be an exothermic process. If this is greater than this is negative, then this will be an endothermic process. So again, the heat of solvation is the energy to and from dissolving the solute. The heat of dissolution is the energy given off by interactions with the solvent. So that's this one right here. Then the lattice energy is the energy needed to break the bonds in this crystal lattice right here. And so those are the enthalpic considerations we have to take when we are thinking about dissolving something. So entropy is often going to be dictated by what's called the hydrophobic effect. And so this is something that you see when you try mixing like vegetable oil and water, for instance. So say we have these hydrophobic molecules here. So we have two of them right here and they get surrounded by water. So the water molecules forms an ordered structure around two hydrophobic molecules. But if we then have these hydrophobic molecules come and interact with each other, we can eject some of these water molecules here and bring these two hydrophobic molecules together. And so we have fewer water molecules forming that ordered structure around the two hydrophobic molecules. And so that is entropically favorable to go from this which has more ordered structure to this which has less ordered structure, because we have removed some of the water molecules involved in that ordered structure. But then we can bring in a third one here, and now we have made this complex here of these three hydrophobic molecules, and we've removed even more water from it. And so we've gotten rid of even more of that ordered structure, and so that's even entropically even more favorable. And you can see we could just continue doing this over and over again until we end up with all of the hydrophobic molecules interacting with each other and interacting as little as possible with the water. And so that's why, for instance, your vegetable oil and water will separate, because it's more entropically favorable. Then the oil floats to the top just because of density considerations. But if we're just looking at this entropy consideration here, it just has to do with reducing the amount of ordered caging around these hydrophobic molecules. So I put this one here just to show this is a three-dimensional process here, where this on the left is where we have our two hydrophobic molecules, and we have these water molecules forming this ordered cage around it. But then we can bring these two hydrophobic molecules together, and we can start removing some of the water molecules from that caging, and that makes it more entropically favorable. And so, like I said, this is a three-dimensional process going on here, where the figure that I made only looks like it's in 2 dimensions. And so what we're thinking about here is two processes, again, similar to what we had with the enthalpy. So we think about this in terms of creation of a cavity. So we take one of these solvent molecules here, we remove it so that we end up with a cavity right here, and then we insert the solute. And so this is probably not the way that it actually happens, but this is the model that we can break it down into when we want to take these delta G's into consideration. So we have delta G1 and delta G2. So delta G1 is making the cavity in our solvent, then delta G2 is inserting our solute into that cavity, and adding both of those delta G's up will get us the delta G for dissolving this solute. So like I said, delta G1 is the free energy to open a cavity in water, so that's this one right here. So we're breaking the strong cohesive intermolecular interactions with water, so we have to break the hydrogen bonds between water apart in order to make this cavity, and so that's going to be our delta H1, breaking those hydrogen bonds between water. And that creates a void against a constant pressure and reducing the configurational entropy of the water. And so this is going to be entropically favorable here. But the delta G1 is going to be large and positive, because creating this cavity here is obviously going to be very thermodynamically unfavorable, because we don't see just cavities opening up in water all the time. So in atomistic models, cavities for biomolecules are commonly defined through the solute's solvent accessible area. So that's what this figure is showing here. So the way we do it is we take this probe sphere that has a radius of 1.4 angstroms, and we sort of roll it around this entire molecule. And the line traced out by the center of this circle is going to be the solvent accessible surface area, or the SASA. All right, so now we can look at the delta G2, which is this step right here, which is actually inserting the solute into that cavity. So free energy to insert the solute into the cavity, turn on the interactions between the solute and solvent, so that's forming the interactions, the intermolecular interactions between the solvent and solute. So that's going to be our delta H consideration there. Ion and polar solvation is usually dominated by this term, so the delta H of that term. This includes the favorable electrostatic and H-bond interactions. It also can include a restructuring of the solute and or solvent at their surface due to the new charges. The simplest treatment of this process describes the solvent purely as a homogeneous dielectric medium and the solute as a simple sphere or cavity embedded with point charges or dipoles. So again, this is that model that we're talking about that allows us to sort of break this up into two different processes here. The opening of the cavity and the insertion of the solute. All right, so partitioning is the thing, like I said earlier in the video. This is an empirical way of coming up with solubility for a different molecule, and it's really the best way. It'd be nice if we had an a priori way to do this, but this is going to be the best way because, as I said, the dipole moments and things like that isn't always going to be the best predictor of whether something is soluble or not. And so here we're just looking at, we can look at a C for the undissolved, so whatever species this is, so maybe it's something like sucrose. And so we have it undissolved just in your tablespoon, you put it into your coffee or tea or whatever, and it dissolves. And so we can have our KSP be equal to the concentration of the dissolved. And so we can then take that KSP for dissolved in, say, water or in some organic layer, and we get the KSPs for both of those. We divide them, and that's how we get this KD here, which is going to be proportional to our partition coefficient. And so this is just going to be the concentration dissolved in organic divided by the concentration dissolved in water. And so, as I talked about in the solvent video, a system for doing this is the octanol water partition coefficient. So the ratio of a chemical's concentration in N-octanol phase to its concentration in the aqueous phase of a two-phase octanol water system. This is often expressed as a logarithm of P here, so it's just the logarithm of this ratio here of the concentration in octanol over the concentration in water. So the more negative, the more soluble in water it is, because that's in the denominator here. So if the denominator is larger than the numerator in a logarithm, it becomes negative. The more positive, the more soluble in N-octanol. So typical range is between -3 for something that's very hydrophilic and +10 for something that's very hydrophobic. And so these are just the molecules here. We have our water and our N-octanol. And so we can think about it this way, where we have our N-octanol phase and our water phase, and we just look at the concentration in the N-octanol, which in this case we have 8, so we put the 8 there. In the water phase we have 10 here, so we put 10 right there, and this ends up being a -0.1, which makes sense. There's more of it in the water than there is in the N-octanol, and so this would make this solute somewhat hydrophilic. In this example, I'm just looking at the number of solute particles, so that would just be assuming that the volume in both cases is exactly the same. If it's not, you'd want to do concentrations for this. But anyway, that is the N-octanol water partition coefficient. And so we can think about the partitioning here in a little bit more thermodynamic detail. So we have some molecule here, this X, which is solid in the oil, and we have this moving into the water here and dissolving into the water. So the equilibrium between the molecule in its solid form and its solution is quantified through the solubility product, which depends on the free energy change transferring between these phases. So we're looking at the transfer of it going from the oil phase into the water phase, where the oil could just be our N-octanol. So we get our P for the partitioning here, which is just the concentration in the organic over the concentration in the water here. So we get the delta G for the transfer between those two phases there. So the transfer free energy, so the most common empirical way of quantifying hydrophobicity, as I said, is to measure the partitioning of a solute between oil and water. So the partitioning coefficient is related to the free energy needed to transfer a solute from the nonpolar solvent, like I said, typically octanol, to water. So the rule of thumb here, though, is just that if you have more than four carbons, then it will be insoluble in water. So if your molecule here has more than four carbons, especially if it's linear, if you start getting into branched things, this rule of thumb starts breaking down. If we're thinking about just linear hydrocarbon chains, then if this has more than four, then it's going to be more soluble in the oil. And so transferring into the water is going to be a positive delta G and therefore unfavorable. All right, so we do, even though, like I said, it's this empirical measure of the partition coefficient that's really our best way of thinking about the relative solubility of things, but we do want to be able to, at least to a first order approximation, predict the solubility behavior of our solutes here. And so general rule, you probably learned this in Gen Chem, like dissolves like. So polar solvents will dissolve polar molecules, and nonpolar solvents will dissolve nonpolar molecules. And so this is just looking at the London dispersion forces here. So we have these two molecules here, these two saturated hydrocarbons. Those have multiple or maximized area for interaction. So these things, I always liken it to Velcro, where if you have just a single loop and hook, it's going to be very easy to pull that apart. But when you have, millions of them, it gets harder to pull that Velcro apart. So we can think of these LDFs here as like Velcro hooks and loops going together. If you have an unsaturated hydrocarbon here, we get this bend in it, and so that's going to reduce the area of interaction. So we see here this only has the three arrows right here, where when it is saturated, then we have multiple arrows there. And similar when we have these molecules of different sizes here, we get these reduced areas for interactions. All hydrocarbons are nonpolar, so this is just a general rule to think about. So anything that only has carbons and hydrogens, you can always just assume that it's nonpolar. However, hydrocarbons like benzene are slightly more polar than hexane because of these pi bonds, which are more loosely held to the carbon atoms, and so there's a bit more room for it to have those transient dipole moments, and so that makes it slightly more polar than just a saturated hydrocarbon. Compounds with oxygen and nitrogen are often polar. So again, polarity depends on the presence of the CO, C double bond O, OH, NH, and CN bonds, shape of the molecule, and the amount of hydrocarbon character. So for instance, if we have something like our ethanol here, where we have this OH bond here, that's going to make it polar, but we do have some hydrocarbon chain right here. And so that's going to reduce the polarity. If we started adding even more hydrocarbons onto here, that's going to reduce its polarity even more. And so the amount of hydrocarbon character that something has is going to reduce the polarity, even if it does have an oxygen or a nitrogen or an OH or anything like that bound to it. And so acetone here, again, this is why these dipoles are not really great measures of how much it's going to act like a polar solvent, but we can see that this acetone has more hydrocarbons on it. And so that's going to make it act less like a polar solvent than something like water. And so halogens do not significantly alter polarity. And so this is one of those things that can be a little bit confusing because these halogens can have quite high electronegativities compared to carbon, for instance, which has 2.5, where fluorine has 4, which is the highest electronegativity. We see that when we get to chlorine, bromine, and iodine, that it starts making a little bit more sense why this would not alter the polarity very much. And so these carbons with these halogens bound to them are not going to be significantly more polar than just a regular hydrocarbon. And so we can see here we have methanol, which is just the hydrocarbon of the relatively same size, and this has a water solubility of 2.27 times 10 to the negative 5. So that's very insoluble in water. Where methanol here we see is extremely soluble in water. So it's soluble in water at all proportions. And so all we've done here is just add that oxygen onto it, and that made it completely soluble in water as compared to the methane, which is extremely insoluble in water. Then we have methylamine, so now we have a nitrogen here rather than the oxygen, and this is fairly soluble in water. So we can put 1 gram per milliliter, so that's actually quite soluble in water. We can then look at putting just a single halogen on each of these. So fluorine, chlorine, bromine, and iodine here. And we see that this does not significantly, well, I guess it's several orders of magnitude compared to the methane, which is 10 to the negative 5. But these are still 10 to the negative 3, 10 to the negative 3, 10 to the negative 4, or 2 rather, and 10 to the negative 2. And so those are still quite insoluble in water. And so there's also this weird thing here where it looks like the fluorine should be more soluble, the fluorinated hydrocarbon, since it has such a large dipole moment when we compare it there. So this is a dipole moment. So this has a electronegativity of 4, but this is actually less soluble than the bromine and iodine, and that has more to do with the size of these atoms. So the fluorine atom is going to be something that's very small like this, where something like iodine is going to be much bigger in comparison. And so this larger one here, we often call these soft, and the reason we call them that is because this large electron cloud has a lot more places where it can form those transient dipoles on it, and that will actually help it to interact better with water. And so that's why something like this, where it has the iodine bound to it, is actually going to be more soluble in water than something with the fluorine bound to it, even though the fluorine is much more electronegative than the iodine. All right, so adding carbons to the chain decreases polarity. So when comparing compounds within the same family, so if we're looking at just alcohols, adding carbon atoms to the chain decreases polarity. And so increasing chain lengths makes the compound more hydrocarbon-like. And so this is that rule of thumb I was talking about here, where if it has fewer than 4 carbons, then it's soluble in water. If it has greater than 6 carbons, it's considered insoluble in water. 5 and 6 carbons can be borderline. And so we can look at the solubilities here for methanol, ethanol, and propanol, which are infinitely soluble in water. So you can mix as much of those into water as you want and it will dissolve. Then we can see, starting at the butanol at this 4 carbons here, we start getting much more insoluble in water, and as we go down this list here, it keeps getting more and more insoluble, to the point where when we get to the nonanol, which is the 9 carbon chain on an alcohol, this is completely insoluble in water. And so, as I said, the general rule here that adding more hydrocarbon chain parts onto the hydrocarbon chain is going to make it less soluble in water. Hydrogen bonding is the strongest dipole-dipole, as I said earlier. So compounds with fluorine hydrogen, which is just going to be hydrofluoric acid, and then OH and NH, which is why usually these are the only 2 listed here for hydrogen bonding, since once you bond this hydrogen to fluorine, then that's all it is. You can't then put that onto other things. So this OH and NH here are our hydrogen bond donors and acceptors. And so what I mean by that is, in a hydrogen bond, so if we have an O to an H, and then we have another O here going to some R group, so this is on some R group right here, we have this hydrogen bonding going on here, where this hydrogen is called the donor group, and this one is called the acceptor group. And so if we have just ROH here, so R O, and H. Then we have another H, O, and R, so these are the same things. This can both act as a donor and an acceptor. And so if you have things that have the OH or NH, then those can act as hydrogen bond donors and acceptors. And so such compounds can therefore always engage in hydrogen bonding. Whereas if we have compounds like this, where if we have an ether, or if we have a ketone, or if we have this tertiary amine right here, these can act as hydrogen bond acceptors in the presence of hydrogen bond donors, but these are not hydrogen bond donors themselves. And so, for instance, if we have something like this, like this ketone here, and we put this in something like this can hydrogen bond donor here. This can actually be our donor here, but this can only be an acceptor. And so that means if we just have this acetone right here, just by itself, these are not going to engage in hydrogen bonds with each other. They can only engage in hydrogen bonds with something that is also a hydrogen bond donor. So the solubility of these compounds is, again, going to be subject to this R chain rule up here, so this hydrocarbon chain rule up here. So then we also want to take alkyl chain branching into account. So as I said earlier, that hydrocarbon chain length rule of less than 4 is going to apply only to the linear chains. Once we start having branching, then we get different solubility behavior occurring. And so these are all going to be 4-carbon, these are all 4-carbon molecules right here, where we see when we have the 1-butanol, so that's the linear chain, this is 0.009 grams per milliliter that can dissolve in water. But then when we get to isobutanol, where now we have a branching on here rather than just a linear chain, we now increase the solubility by an order of magnitude right here, so almost 0.085 grams per milliliter. Then when we have this sec-butanol, which is even more branched here, so we have one branch coming off on this side, another branch coming off on this side, we now go up and get another order of magnitude in our solubility, 0.125 grams per milliliter. Then when we get to the most branched one, which is this tert-butanol right here, this now becomes infinitely soluble in water. So you can dissolve as much of that into water as you want, even though all of these have the same number of carbon hydrogen groups on them. These have different solubilities in water because of those branches occurring. And so again, like I said, when we think about this up here, this rule of thumb, this really only applies to things that are linear rather than branched. When you start getting branched, you start increasing water solubility, but there will be a point at which it becomes insoluble in water again if you start adding enough of these hydrocarbon groups to it. And so another thing to consider is that like dissolves like within a family of molecules. So within the same family, so again, let's think about alcohols here. The solubility between longer chains and shorter chains is greater than with compounds from another group. And so what I mean by that is, say we have one octanol here, which is an 8-carbon chain with a molecular weight of 130.23 grams per mole, is soluble in a solvent of ethanol, which is a 2-carbon chain and a much smaller molecular weight, but not in water. And so ethanol, we saw earlier, is infinitely soluble in water, but N-octanol, or 1-octanol, is not soluble in water. It's very insoluble in water. Yet N-octanol, this 1-octanol, can dissolve in ethanol. And so there isn't like a good transitive property here. So, the transitive property being that if N-octanol is soluble in ethanol and ethanol is soluble in H2O, we can't then conclude that N-octanol is soluble in H2O. So we know that that's not soluble, even though this is soluble in ethanol and ethanol is soluble in water. N-octanol is not soluble in water. And that's because this N-octanol and the ethanol are both within this same family of alcohols. This, however, is not infinitely extendable. So, for example, a very large alcohol like cholesterol, which has C27H45, then a single alcohol group on it, is only slightly soluble in methanol. So, around 0.01 grams per milliliter at 20 degrees Celsius. But the idea is that within a family of molecules, such as the alcohols, you do get this sort of extra solubility occurring that would not be predictable just based on if we wanted to use some sort of transitive property of solubility here. All right, and so solubility and melting, so other things being equal, so things like molecular weight, number of carbons, and functional groups, the higher the melting point, so the more stable the crystal, the less soluble the compound will be. So for example, this para-nitrobenzoic acid, which has a melting point of 242 degrees Celsius, is less soluble in ethanol than this ortho or meta nitrobenzoic acid, which has this lower, these both have lower melting points here. And so this p-nitrobenzoic acid is soluble in ethanol at 0.009 grams per milliliter, where the meta, I wasn't able to find anything for the orthonitrobenzoic acid solubility, but the meta, the M-nitrobenzoic acid, is 2 orders of magnitude more soluble in ethanol than is the para-nitrobenzoic acid. And so we see that sort of in general, having a higher melting point with everything else being equal, the molecular weight, number of carbons and functional groups and everything, anything that has a higher melting point in general is going to be less soluble than something that has a lower melting point. And that's because these things are based on some very similar concepts about the way that these things interact with each other. If they interact with each other more strongly, the melting point is going to be increased. That also means it will take more energy to break them apart when you are trying to dissolve them, and so they become less soluble. And so we can see here, so this is the solvent type. And so this is just a general rule here for our solubilities. So we have up here, this is going to be our most polar, so we have the highest polarity at the top and the least polar at the bottom. And so this is kind of, like I said, a very loose and general rule. As we saw above, there are plenty of other considerations to take into account, but we can think of water as being our most polar solvent, then organic acids like acetic acid being the next most polar, and then working our way down until we get to the alkanes here, which are just the pure hydrocarbons. And so those are going to be our solvent types there. So we can also think of ion solubility. So for most practical purposes, any organic compound in an ionic form will be soluble in water. And I'm mentioning this because this is important when it comes to things like liquid-liquid extractions, which I'll get to in a future video. And so if we have octanoic acid here, which has a water solubility on the order of 10 to the negative 5, when you deprotonate this, say with this hydroxide here, then you get this ion. So we have a negatively charged ion. This is now 100% infinitely soluble in water. And so just putting this charge on here, we now have these ion dipole bonds with water. This becomes soluble in water. And we can do the same thing with amines as well. So if we have this one amino octane here, this is very insoluble in water. We protonate it with this hydronium here, so with an acid, then this becomes infinitely water soluble here. And so that is going to be a useful tool, as we'll see in future videos, for doing liquid-liquid extractions. One last thing to mention, and this is something I'll get into in a lot more detail in the next video, is solubility in temperature. So generally, substances are more soluble at higher temperatures. So you heat something up and all the solutes will become more soluble in it. And so we see that we have our KSP here equal to this E to the power of negative delta G over RT. So we're looking at this temperature term right here. We see that KSP is proportional to E of negative 1 over T. And so it's proportional to 1 over E of 1 over T. And so we see that as temperature goes up, this goes down. And so this goes up right here, since this is in the denominator. And so that means that our KSP, our solubility, goes up as temperature goes up. Like I said, I will discuss that in more detail in the next video, which will be about crystallization. But anyway, this video is already getting quite long. I hope you found it helpful, and I will see you in the next one.